Okay, so picking up from where we left in the last section, so I defined what a signal, so a brief recap. So I defined what a signal was, and we looked at two broad classifications of a signal. So one is the continuous time signals, and the another one is a analog signals as well as the digital signals. And we saw that in analog signals there were two kinds that we are mainly interested in. So we characterize signals as a functions of time only. The independent variable was only time when we described it mathematically. So in analog signals there were two kinds. One is the continuous time and the second one was the discrete time signals. So the other one was digital signals. So where your y-axis as well as x-axis could take only discrete values, right? Our x-axis was indicated with n, which is the index, and our y-axis as usual was x of n. Okay, so both could take only discrete values, not the continuum of values. So that's what the distinction between the two kinds of signals was. Okay, so from moving on from there, so today we'll look at systems. Okay, so a system can mathematically be described as a transformation acting on a signal. Okay, and broadly we'll look at two kinds of systems. One is the continuous time systems. Okay, and the discrete time systems. Okay, so discrete time as well as digital systems, right? So there is a small difference, so no need to go into the difference between both now. Okay, so and there is an intermediate kind of systems where the input will be analog and the output will be a digital signal, and the other way around, right? The input being digital and the output being a analog signal. So we'll not look into those. So the two kinds of systems that we'll look at in this workshop will be continuous time systems and discrete time systems. So as I told you, mathematically the system can be described by a transformation. Okay, so I have a system S, right? So this is a block diagram representation. So I have a system S, right? On the one side, so there is an arrow that is pointing towards the box, which is nothing but the input to the system, which usually we use the term X. Okay, and on the other side you can see, so the direction of arrow represents the direction of flow of the signal, right? So the X of t, the signal X of t is moving into the system, and another arrow you can see here is coming out of the system, which we call it as a output, right? So our usual terms, so in this case X of t is the input to the system, input signal to the system. S is the system, it's just a name, right? Depending on the function, the system S can be classified, right? And Y of t is the output. Okay, output signal, so if you will. Okay, right? Now so the important class of systems that we are going to look at in this course are basically the stable systems. So I'll define stability when and where the topic comes up. Okay, the other two properties that we are looking at is the linearity property of a system as well as the time invariance. Okay, so time invariance, broadly you can tell that, okay, if you take a system, so you feed a signal X of t today, right, and note down what the output is, the corresponding output Y of t, let's say. Okay, and you wait for one day, right, and tomorrow you feed the same input to the system, right? If you get the same output tomorrow when you pass the same signal through the same system, right, the system can be called as a time invariant system. Okay, fine. So that was a broad definition of the time invariance. Of course I will define it mathematically now. Okay, so okay, so let's dive into the linearity property. Okay, so a system is said to be linear if it satisfies two principles, right? So one is the principle of homogeneity, okay, and second the principle of superposition. Right? So now before moving on, I'm not going to draw the same diagram again and again whenever I take the input and output signals. So I'm going to use the shorthand notation, right? So my shorthand notation will be this, right? So this notation, so you can see that I have drawn an arrow that is pointing from x of t to y of t, and on the top I have written s. So this notation implies that this, when x of t is passed through a system s, it will give rise to an input, give rise to an output y of t. Okay. Now suppose I have a system s. Okay. So what is principle of homogeneity? Suppose, so first one, so I'll explain the principle of homogeneity. Suppose if I take x of t, right? So let's say x1 of t, I'll pass it through a system, say s. Okay. And let's say I note down the output, and let's say I call the output y1 of t, right? Now through the same system s, if I pass the magnified version or the attenuated version, a is just a constant, right? So if a is equal to 2, the signal 2 times x1 of t will be twice as large. Okay, so the amplified version of x1 of t, right? If I pass it through a system, my output should be the amplified version of the output in the previous case. Okay, so the constant term here, the scalar constant here, right, should be preserved, right? So the output will also be magnified by the same amount, okay, as that of the input, right? So a is a constant here, it's not a function of time, right? A is a constant number, it might be complex or real, right? Okay, moving on. Next, let's look at what the principle of superposition tells me. Okay, suppose I have a signal x1 of t, I pass it through a system s, and I'll note down the output. Let's say I'll call the output as y1 of t. Okay, now I take another signal. Okay, let's say I call it as x2 of t, which is different from x1 of t, of course. Okay, I'll pass it through a same system s, and I note down the output. Let's say I get the output some y2 of t, right? The signals here in this, throughout this workshop, we'll be taking them as a functions of time. Okay, now when I superpose both of the inputs, okay, and let's say I define a new signal x of t as the superposition of the two inputs, okay, which I passed in the previous case. Okay, I took x1 of t and added it with x2 of t. I call the new signal as x of t. Now if I pass, okay, x of t through the same system, right, and I note down the output, okay, I'll call the output as y of t, right? If this y of t is equal to the sum of the two outputs corresponding to x1 of t as well as to x2 of t, then the principle of superposition is satisfied. Okay, if the system satisfies these two conditions, these two principles, basically the principle of homogeneity as well as the principle of superposition, right, we say that the system is linear system. Okay, fine. Let's take an example of a linear system. Let's say I have an amplifier, okay, an ideal amplifier, right? let's say the gain of an amplifier is 3. Okay, so A is called as a gain of an amplifier. So I feed the input here and the output I take it here. Okay, so suppose say let's x1 of t be equal to cos omega 1 t, right? And let's say x2 of t will be equal to sine omega 2 t, right? So I pass these two signals, so my output corresponding to x1 of t will be, so I'll call this amplifier a system S. Okay, my output will be, since it's an ideal amplifier, it will be 3 cos omega 1 t. Okay, and similarly when I pass this input to the same system, the amplifier, so my output will be what? So it will be 3 sine omega 2 t. Okay, now if I pass some alpha times x1 of t plus some beta times x2 of t, okay, through the same system, what do I get? I get 3 times, so let's call this a signal x of t. Okay, so I'll pass it through the same system, so I'll get 3 times x of t, which is nothing but 3 times alpha x1 of t, right, plus beta x2 of t, right? It's an amplifier, so it amplifies the whatever the signal it is by 3, by a factor of 3. Okay, so this will be equal to, right, so alpha times 3x1 of t plus beta times 3x2 of t, right, which is nothing but alpha y1 of t plus beta y2 of t. Okay, so if you note here, right, so y1 of t was the output corresponding to x1 of t, and y2 of t was the output, y2 of t was the output corresponding to x2 of t. I'm sorry, right? So the scalar constants alpha and beta were preserved, right? So this system satisfies the principle of homogeneity as well as principle of superposition, as you can see in this equation, right? So alpha and beta are conserved, okay, or preserved, right? So this system is a linear system. An ideal amplifier is a linear system, okay, because it satisfies both the principles, the principle of homogeneity as well as the principle of superposition. Okay. Moving on, the just as an example, suppose I have a system S. Okay, so I feed a signal x of t, right, and I get a signal y of t, right. So the relation between x of t and y of t, let's say is y of t will be the square of the input signal. Okay, so then you can work it out, show that or prove that this system is non-linear. Okay, so just check the two principles. So you can see that the both one of the principles will not be satisfied, the principle of superposition, right. So this system will be a non-linear system, right. Even the principle of homogeneity won't be satisfied, so you can prove that and show that the system is non-linear. Okay, so work it out and prove this result. Okay, so the system is non-linear, what I have given. Okay, so by definition, okay, so this system, right, the system can be defined mathematically as, so I have a system S. Okay, here, right? So the what system basically does is it acts on a signal x of t and transforms it to another signal y of t. Okay, so the parameter here or the argument here will be x of t. It's basically a transformation acting on x of t. You can call it argument or whatever, right? The output y of t depends on the input signal x of t, right? So we'll look at the property of time invariance in the next session.